Moc krát děkuji, pane proděkane, za představení. Vážení členové vědecké rady, děkuji, že jste přišli. Moc děkuji profesoru Matasovi a celé komisi za čas, které na přihlášce strávili, a vážím si příležitosti, že se mohu ucházet o profesorství na ČVUT. Slíbil jsem kolegům, kteří nemluví česky, že budu mluvit anglicky, so I'll switch to English for the rest of the talk. And I will start with my background. So I came to the Czech Republic after more than 15 years abroad. I did my master's degree here at ČVUT, but then spent time in the UK, US and France. And I came back on the Come From Abroad grant, so which allowed me to build, and I lead now a team of about 15 people doing research in computer vision, robotics, and you will also see at interdisciplinary machine learning for molecular biology. The project has finished, and I was fortunate enough to also have to continue the work to receive an advanced ERC grant. So I will actually spend most of the presentation showing you the objective of this project and some of our research highlights, which we have in this direction. The project is not finished yet, so some of it will be ongoing work. So computer vision, I find it very exciting because visual sensors are used as one of the primary inputs of a range of current and future embodied systems that interact with the physical world around us. From robots in logistics at home, in construction or outdoors, in personal assistance in industry or for everyday tasks. So what is interesting that these systems encounter embodied visual experiences in many different environments and situations. Now imagine that these systems could learn from each other's successes or mistakes by sharing or federating their embodied perception experiences. So now I would like to argue that such federated embodied perception presents the new frontier for computer vision. And for example, wouldn't it be great if these systems could collectively learn sequences of manipulation actions to achieve complex tasks, such as changing a car tire, by interacting with many different car types in different environments, and then perform these tasks in new setups or to assist non-expert users in their environments. So such federated embodied perception would be a step really towards a revolution in manufacturing, for example, where automatic workers could achieve new levels of capabilities by learning new skills from each other and to automate heavy tasks which are currently done by humans. But also, while we have seen revolution in automatic diagnoses by achieving almost superhuman performance by sort of aggregating experiences from different doctors, automatic robotic surgery still remains largely out of reach, as it requires these embodied interactions with the patient. But imagine what if surgical robots could collectively learn from their failures and successes to enable this next step in automatic surgery. So recently we have seen truly impressive demonstrations of scaling up neural networks into so-called foundation models, which have really marked a paradigm shift in natural language processing and computer vision, where a single large-scale neural network with hundreds of billions of parameters can act as a foundation for a wide range of downstream tasks, such as generating computer programs, as you see on the top, or synthesizing complex high-quality imagery. So while this progress is truly amazing, at the same time we still do not have machines that could reliably empty a dishwasher at your homes or perform all cooking tasks that a 10-year-old can do in the kitchen. So the issue is that the current state-of-the-art foundation models, they really represent mainly 2D image patterns, like image patches, or really have a limited temporal context. Do not model the embodied interactions requiring the physical consistency and completing multi-step tasks. These models are also trained on large-scale offline data sets and require supercomputer infrastructures. So what we propose in this project is to shift the focus from learning from these large-scale offline pre-collected data sets to new type of models that can federate physically plausible 3D perception models, which are learned across many different systems, thereby achieving really new levels of scale, accuracy, and robustness, not achievable by any individual system alone, or by learning from large-scale offline collected data. So really to tackle this challenge, we have been working in 3 different main scientific directions, which I will now explain and show you some of our research highlights in each of these directions. So the first scientific question is, what is the right architecture for this embodied perception? Most current foundation models, they really learn only 2D image representation. So the key problem is how to incorporate in the model the physical interactions with the environment. And so what we've been working on are new model architectures that explicitly represent the geometry and physics of the infrared 3D scene objects, here in the notation S, contact C, and the forces U, that explain the measured visual features Z by solving the following optimization problem, where the data loss measures how well the infrared 3D dynamic scene matches the observed visual features Z over time, which is here the sum over T number of frames. So while these physical constraints are commonly used in robotics, the key innovation here is to incorporate these constraints in the visual model architectures. And the main questions we are looking at is, what is the appropriate form of these constraints, how to implement these constraints in the neural architecture. So here is an example highlight of work in this direction, where the visual input is on the left. It's a frame from a video from YouTube. And our model outputs 3D interpretation of the scene, which you see on the right, which includes both the person as a form of a skeleton and the object, together with the estimates of the contact forces shown by the yellow arrows between both the person and the ground and the person and the model of the object. So now these results open up the possibility of incorporating these physical constraints in these models of visual data. We are very happy because this work was selected among the best paper finalists among several thousand submissions in one of the largest conferences in computer vision. So while this is very exciting, this work was limited only to stick-like objects. So we were looking how to extend it to developing models which can reliably localize and recognize 3D objects in images. So we really have a line of work building the 3D building models which can estimate the 3D poses of objects in complex input scenes, as you see in the top row, which can predict the location of the object and its 3D pose, which you see in the middle row, and then the whole scene is visualized in the bottom row. So these are very hard problems because the scene contains multiple objects, often textureless, as you see in the second column, with multiple heavy occlusions as well as self-similarities, as you see on the column in the right. So we've developed a series of large-scale neural architectures which are trained on millions of synthetically generated imagery, which capture all these challenging scenarios. And we are one of the first to approach the problem in this way. And Merrill managed to outperform all the existing methods on that problem by a large margin, there's a challenge and competition on this problem, and we at the time really won all the different sort of sub-competition with this model. So what this allows us now, when we have it, it allows us now to really impose the different constraints between the objects when we estimate the scene. So this is a very much sort of more recent work where we are looking at, so once we estimate the poses, enforcing the constraints such as collisions and gravity on the scene. And here is an example of, on the left you can see the input image, and on the right is a video of how the optimization goes, where it's coming up with the physically plausible interpretation of the scene without self-collisions or without collisions, and incorporating the contacts with the surface. So as you see, so some of the penetration sort of goes away because we can incorporate these constraints. We also try to be good members of the scientific community and publish most of our methods open source for reproducibility of the results. So this is one of our latest or later version of the method, which also sort of won, but in this case, the best open source method in the challenge. And what is exciting is that we can see our methods being used by others. So although this is unofficial, but we heard rumors that the system here built, this is the famous Atlas robot from Boston Dynamics, has been building on our work to estimate poses of objects. So you see the robot here grasping an object. You can see the pose estimates here. And it's doing fairly impressive full body bimanual manipulation and inserting the object to a pre-specified place. So this is so far what I consider one of the most impressive demonstrations of like a full body manipulation with two hands of the object. You can see the video in the with a from external viewpoint. So once we have the sort of CD interpretation, the second main scientific question we've been looking at is how to formulate the learning problem. And here, the main problem is how to learn these embodied perception models for tasks that require multi-step interactions that change the states of the environment, such as you can see in this example where we have complex interaction with the environment. And so what we proposed is to extend the self-supervised learning, which is the workhorse of the current foundation models, with causal ordering and planning constraints to really learn these multi-step plans. So given a set of visual inputs xi and metadata yi, the goal is to learn maps f and g by minimizing a loss on data that measures the discrepancy between the model prediction and the latent representation z, which is constrained by the supervision from the metadata here. So the key innovation is to incorporate in the learning these physical and ordering constraints via this mapping H. And the main scientific question are what is the appropriate form of this map H and how to formulate these constraints. And ideally, we would like to not set the constraints by hand, by sort of learn them from the data. Although we are not there yet at the moment, we set up these constraints by hand to encode, say, the physics or the priors about the problem. So we have exciting results in this direction. So we've developed a machine learning series, a series of papers looking at the machine learning models that incorporate these ordering constraints, which are shown here at the bottom in the blue, to learn how states of objects change because of human actions when people interact with the scene, such as when you see the candle here goes from dark to lit because the person is sort of doing this change. So what this allowed us, so once we can do this on a large scale, what this allowed us is that in this line of work, after we learn to localize and recognize these object states and the changes and the actions, we can train predictive models. Sometimes also they are recently called world models that predict or simulate how the scene would be changing as a result of multi-step human actions. As shown here, on the left is an input image. On the right are natural language instructions, and what you see is a series of images, how the scene would be changing by these actions. And of course, from a single image, one can do sort of different instructions to do sort of different changes, and for different input image, one would get, with the same instructions, sort of different images. And this is difficult because one has to precisely capture the changes of object states, yet preserve the scene consistency. What is here, our model can do this for much longer sequences than current existing models. And this is also because we are encoding only a sparse set of keyframes rather than modeling the whole temporal continuity of the video. Okay, so the third main scientific challenge we've been looking at is how to formulate and solve this federated embodied learning problem. So in particular, how to formulate that, we are given a set of now M embodied systems indexed by K, where each system observes visual inputs xi with metadata yi, but it's specific for the system K here now. And what we wish to extend this formulation, which you've seen in the previous objective, but now extend it to this federated learning setup, where our goal is to learn these maps F, G, and H that are shared across all the systems, but minimizing by a weighted sum of data losses locally in each of these systems. So this is a hard problem, and one of the key issues we are encountering, as everybody else, is that how to aggregate these model parameter updates, FK, across heterogeneous systems which are operating in different environments, such as the person on the left here and the robot on the right, which are doing sort of the same action but in a very different manner, or across different even tasks, such as here the robot doing the sort of shoveling the material and pouring action at the bottom. So the key challenge is how to federate these local parameter updates. One can formulate it by some kind of a map psi here into a single consistent model. And some of the key scientific questions are: what is the appropriate form of this mapping? Can we learn psi together with FG and H from data? And how to solve this problem for many systems. This is very much ongoing work. We have some initial solutions which are sort of using simple, again, geometric aggregation, but the learning this mapping automatically, I think, is still quite far out. Yet we have some example preliminary results in this direction, where given a visual input on the left, we learn a policy for this task, which you see on the right, on a real robot, which is a very different morphology. And the key to this is that we are not looking at the motion of the person or the robot, but motion of the tool. And then we can use sort of more standard, say, inverse kinematic techniques to recompute the appropriate motion for the specific robot. This allows us to sort of aggregate, to perform this also on very different robots with different morphologies. And again, it's because we are focusing on the tool motion rather than the motion of the people. Of the person. So, and so there are many different issues in this generalization. I see one of the key open problems in current perception and robotics, how to generalize across embodiments, across tasks and environments. And while we don't have the solution, we thought, well, the key thing first is to be able to measure progress on this. So we've developed a real-to-sim validated benchmark for generalization robot manipulation. It's done in it's a simulated environment, but it's validated that the results correlate with performance on a real robot. And it allows us now to measure across a range of tasks and now 15 perturbations, which are both visual, semantic, and behavioral. It allows us to measure generalization of the different foundation models for robotic perception, for robotic manipulation. Okay, so at the moment, what we've been looking at are robotic systems that operate in our physical world around us. But there are also very much interesting systems in the world of molecules, and here is an example of a transport protein called kinesin, which is transporting, here's an illustration, transporting cargo inside a cell. And so more generally, so proteins are some of the key building blocks in the human body. So you may know them as important nutrients, but they just don't build the mass in our body. They have very important function. They can exhibit dynamics, as you've seen here in this protein. There are enzymes. They can transport stuff in our body. If you have a malfunction in protein, which may be involved in a disease like neurodegeneration, it can become a drug target. We can design a small molecule which will bind to the specific protein to fix this function. The proteins, they can be also themselves, they can be drug. This is an example of drug. There can an example of antibody, which is shown here in red, which is a type of protein which can bind to a pathogen like a coronavirus. And destroy it. So despite this huge progress in biology, there are still many biological processes that we just don't understand how they actually operate. For example, just the human brain contains approximately 20,000 different proteins and more than thousands of small molecules or metabolites. And here I see a very exciting opportunity for machine learning to help us understand the proteins and their function and the processes in the human body. You may say, well, why is this interesting? And one example application is to cure disease. For example, I have two here, Alzheimer's disease, which incurs huge costs, It's a 7th leading cause of death globally, and still we don't quite understand what the underlying processes are, and we don't have efficient drugs available. Another example is acute stroke, which is one of the leading causes of death and disability worldwide, yet new, more efficient and inexpensive thrombolytics are needed. So when we began to look into these problems together with our colleagues in biology, we realized that there are many commonalities between the actual machine learning challenges which need to be addressed. So we really made like a research program which is looking at similar objectives which are looking at embodied perception, but in the learning for biology. I will illustrate this on one example problem and then show you where it could potentially lead. So this is a particular project. It's a fairly large-scale effort to develop a new treatment for stroke. It's based on a protein called staphylokinase. The staphylokinase, it's a drug candidate, and it interacts with a protein in blood called plasmin, and it sort of happens, there's some kind of a chain reaction which then dissolves the fibrin clots which are in the blood, which are the clots which block the blood flow. And the key important element of it's a binding that the staphylokinase drug needs to bind to this plasmin to form a complex. So what we've been looking at with our colleagues is this step is how to make the staphylokinase more attracted to plasmin, how to increase this binding to make this process more efficient. So just as a reminder, proteins are made of a vocabulary of 20 amino acids, which are simple biomolecules, which you see here on the left. And once the amino acid sequence is formed, it folds into a complex three-dimensional structure, which is the one which you see on the right. And often it's visualized in this simplified form with sort of these alpha helices, beta sheets, and these another parts. So you often see visualizations like this. So what we are here really looking at is how to make the staphylokinase more attracted to plasmin. So here is an example of the staphylokinase drug, and this is the plasmin in blood, the protein, and here this is a close-up of their interface. And these individual amino acids, they interact with each other. And the question really is what amino acids of the staphylokinase protein we can mutate, we can change, and how to change them to increase the attractiveness, the binding between the two proteins. And it's a difficult problem because if you have n amino acids on the interface and we have 20 possible options at each amino acid location, we have really 20 to n combinations. And if you want to test each combination, you have to go to the lab, and it may take a week or even longer to synthesize the proteins and measure how they bind. So wouldn't it be great if we could sort of predict the effect of the mutation automatically in a much faster way? And just to give you more details on this, really the attractiveness is measured what's called a binding energy, called delta G. And the intuition is that this is the energy which would take to take the two proteins apart from each other. And lower is better in this case. And so what we are looking at, we want to mutate or change specific amino acid on the interface, replace one amino acid with the other. And really we can formulate this as a machine learning problem where we would like to predict the change in the binding energy, change in the delta G, which is referred to delta G, for the specific mutation. It follows this distribution, so the lower is better here for the delta G. Many of these mutations are bad. They will either destroy the protein or just not bind at all. But what we are looking is to predict these gold nuggets, which would really increase the binding energy. So here we are facing this machine learning problem, and now we are facing again these questions, like what is the right architecture first to model these intermolecular interaction. So here we've developed a graph neural network architecture to represent the interface between the two proteins. Here each node of the graph is one specific amino acid, and the edges represent the interactions either inside, between amino acids inside the protein or across the interface. And this way we can really encode the sort of interaction between the two proteins. The second question is how to formulate the learning problem. And so there is training data for this problem. There are databases where people measured in the lab what the effect of the mutation. The problem is that this data is very scarce. So the biggest data set for this problem has 300 interfaces and 7,000 mutations. So it's hard to learn from it. So we are looking what else can we do. And we again looked for inspiration in the techniques which are used to learn large-scale models in language, for example. We looked into self-supervised learning. So for this, we collected what at the time was the largest unlabeled data set of protein-protein interfaces by mining them from the existing databases. So those are just interfaces. They don't have the delta G annotations. But we can synthesize automatically from this data a large scale of millions of sort of mutations. I will show you how. You may know that one of the paradigms which is driving the current language models is what's called masked modeling, where you have a sentence and you train the model to predict a missing word in the sentence. You mask the word and you let the network predict it. So we adapted this techniques now for proteins where we have an interface and we can mask some amino acids on this interface and have the model predict what amino acid should be there. So here in this illustration, the masked amino acids are in gray, and we've developed a loss function which allows us to do that, and a sort of learning technique. So this model, it turns out that if you pre-train it in this way, then performs much better on this delta G task, which we can fine-tune the model afterwards for this task. So we can outperform existing methods on the standard data sets, but what's of course ultimate validation is in the lab here. So this is a picture of the mutants which we designed in a freezer before they were evaluated experimentally. So while this is exciting, we really are on multiple different applications. We are seeing that the data is the problem, that we don't have enough data for the specific task at hand. So I see really going forward, I see really a great opportunity here in developing machine learning models that can autonomously design experiments, execute them on an automatic experimental biological platform, and learn from these interactions. So we are working in this direction currently with our colleagues in biology at the Masaryk University in Brno. And I really truly believe this is a huge opportunity to significantly speed up the progress in biology and more generally in other sciences. So for us, the machine learning for biology is not just one-off project, it's really a new research direction which we are developing. These are some examples of our recent publications in some of the top tier venues in this area. So overall, I feel we are really at a very exciting moment in time where we are on the cusp of sort of seeing systems that can interact with the world and help us understand its nature. So we are making steps towards systems that can autonomously learn, reason, plan, and interact with the physical world around us. And I think what's also even more exciting, while I do believe this is going to take years, this is not going to be something which is going to be here next year or in 2 years. This may take us 10 years before we make significant progress. I do believe that we are going to see exciting applications in specific constraint setups. Like in robotics, while it may be still years away before we make a generic robotic system which can do all the tasks, in specific constraint setup like farming, we may be able to design a system which will significantly help to do human labor. And similarly, why we are far from true understanding of really the process, all the processes in the nature, we may be able to develop a sort of AI-driven drugs or materials. This is all on the science. I would really like to thank the team. Yeah, without them, this really wouldn't be possible. It's really their work. And I would like to highlight also that we try to involve in our research, of course, apart from research and PhD students, also master and bachelor students, because we do think that, and we do involve them in projects so that they can contribute to the top tier papers which we are doing, because we do believe that sort of they can learn by doing the science. And with that, I thank you very much for your attention. And I'm happy to answer any questions, of course.
Yes, thank you for sharing your results, challenges, ideas visions in the field of automated visual recognition. And now I open the floor for the discussions, and please put your questions. Professor Kittler.
Thank you very much for a fascinating lecture. In the section on embodied perception, you talked about the importance of physics and geometry. And similar problem arises in image and video generation, and the current move in that area is from using mathematical models of physics and geometry and replace them by prompts. Do you envisage a similar sort of direction in the case of perception?
Yeah, no, it's a very good question. I think we've been also, I think the way I feel it's moving to currently, and is that these models, it's hard because we need the scale. So that's usually, it's hard because any kind of additional modules enforcing consistency inside a model makes it slower, the learning. So at the moment where it seems to be going, and we are also doing that, is that we let the model to predict, to generate, and then we go and correct its output. We impose the constraints afterwards on this. And of course, one can then take the data, either used with the enforced constraints or feed it back in, either in context setup or actually to fine tune, to improve the model. So you can think of it as a kind of a way of chain of thought reasoning, is that first you input it, then you do the reasoning, then you put it back in the, so I think that's where it's going. It seems to be a good compromise between sort of enforcing the constraints, we have to wait to enforce it, and the efficiency of the learning. Yeah. So I think that the chain of thought is sort of fully consistent with this, but we can now, if we do have, if it's not just the pixels which it generates, but if we have also like the 3D, say, boxes, or we can enforce the constraints on the outputs.
Thank you.
Thank you, and Professor Svoboda.
So, Josef, you mentioned modeling contacts at several places at your presentation. As far as I know, in modeling contact, especially when soft deformable parties are involved, it's particularly hard. Do you really, I mean, how do you work with them? Is it really that you model them explicitly, and how far are you with it? I'm really curious.
Yeah, so by the way, here, we work closely on this domain with our colleagues in robotics, mainly in Laos, in Toulouse, and in Paris. Yeah. So they are developing their own simulators, which we are then using. We're helping them with that, and we are using in our work. I don't know if I have any slides on this, but of course this mainly works for rigid bodies. I think that's where we are at the moment. I think when it's getting soft, I think we are out of sort of at the moment. I mean, there are ways to model this, but it's much more expensive, and we are not doing that at the moment. So, but yet I think there is a way to utilize so modeling the contacts, and we can model different. The models are getting better and better, but of course they are not perfect, and they are not, it's always a model. It's a simplification of the reality. So there is a certain way one can go with it, but I think already this would be or is useful for learning. Now for more the soft part, I think that is also interesting. So we are looking at these kind of, I show lots of results with the cooking. So this is super hard to model because it's all soft, and here I think it's a potential to use machine learning and we are also looking for this learning what's called these dwarf models. So they basically learn how the scene is changing, where it's hard to model physically. So I think it's going to be some kind of a compromise. We'll explore both directions. I will have to see an experiment. And it may be at the beginning we'll see more physics kind of encoded, but eventually get more data, it's going to be more learning. But
okay, thank you.
Děkuji. Professor Železný.
So I understand you predict the protein-protein interactions through graph-based neural networks. I'm assuming this gives you the power of looking at the structure and exploiting the structural information. But what about further background knowledge which have the nature of rules, such as amino acids with opposing charges tend to attract each other? Does does the network-based approach give you the power to also take those into account?
Yeah, it's a good point. Sometimes, of course, one can sort of have it somehow explicitly enforced in the predictions that we don't want some, but often, at least in this work, we sort of rely on the power of learning. So we have some things which we encode, like the position of amino acids, but then we sort of rely on the training data that it does capture kind of the type of in this work. But in other works where we are looking, I'm trying to think, of course, this does come up from the biologists because this shouldn't be like this. Yeah? So there is a place to also enforce it. I'm wondering, I don't think we do it explicitly in the edges, that we would have like explicitly some kind of discard, some connection. I don't think in this work we do it.
So is there hope for including prior knowledge into, let's say, the architecture of the network?
So this is a graph neural network. So by itself already encodes like a certain, one can do it in ways which are this equivariant that one, so it doesn't matter, like permutation variant as well. So, and it is interesting, and it's one of the, I would say, prevailing directions now people are looking at. But what is even more interesting is that some of the latest models, like the AlphaFold 3, for example, they are going away from the graph formulations. They just really represent, it's a sort of diffusion model which just sort of diffuses the coordinates of the atoms, and they basically do like a randomization at the training time. So they take the training data and rotate it from 30 different random rotations. They would put it in the centroid, rotate it from 30 different random rotations, and they don't explicitly model equivariances. Yeah. So I think it is, I don't think it's still like what's going to be the best model. I think people are still exploring more, but we are seeing a little bit going away from the explicit modeling of equivariances to these more, just learn it from the data. If it doesn't contain, just synthesize the data in a way that it have just enough invariants what you need. Yeah.
All right, thank you.
Thank you. Professor Svoboda, once again.
If I may, it's perhaps more a philosophical question, but it caught my attention close to the end of your presentation. You mentioned the ambition of understanding the nature. Okay, maybe I caught it I misinterpreted your statement, but are you talking about really that the, say, artificial intelligence would understand or rather model the nature? Yeah, I mean, it's a fine boundary, of course, but I think what we are seeing, and I didn't have time to, I'll try to explain it now. What we are seeing that one can simulate some processes, but some processes are hard, it's very difficult to simulate with current technology. And simulate, I mean really model the inter-atom interactions. So in the example with the staphylokinase, we started with the binding energy, which is, we can simulate, model that. But then actually what is important down the line is actually the activity of the drug candidate, but this would involve modeling the entire chain reaction of the process, and this is complicated. So actually, what we are doing at the moment, we are collecting training data where we measure for different mutations the actual activity of the protein, which is very difficult to do any simulation on, but we can just go to the lab and measure that. And we are designing kind of a in-the-loop machine learning model which will collect the data and predict what are the next mutations to measure. Every mutation to measure may take weeks, so it's very important to read in a way. And this is just one example. And I think where it's going, and others are also going that direction, is that it will be the model, machine learning model will design better, candidates to measurement than a biologist expert would do, because can gradually learn from these interactions. So on this concrete example, and so we're starting from this, we want to expand this, is that these models will really kind of collect just the data, what they need in the way sort of to predict what property you want. So it's going to be this sort of target. And if you can automate this process as much as possible, so in the Clara project, they are getting this automatic robotic lab. If you can speed it up, you can really have this cycle, which will be continuous measurement and for the task at hand. So we are looking kind of, and then people would say, the narrow AI for specific, I want the best drug for this. Can the system kind of develop it in this measurement? It's called like a design, build, test, and learn cycle. So. Okay, thank you.
Thank you. So are there any other questions? So if not, I would like to thank you, Dr. Šivic, for your very nice lecture, the audience for the participation in the discussion, and I close this lecture session.